Chapter 20, slides 37 to 44. Okay, we have finally reached the functionality of amides and nitriles, but amides specifically, I've been waiting to get to because they play such a large role in biochemistry. What I want you to recall is that the amide is not basic. It is neutral. Just like an aldehyde or a ketone, an alcohol, it is, if you took an amide molecule, say this anandamide down below, found in chocolate. Notice that there's double bonds, there's an amide, and there's an alcohol. This molecule, if placed into a solution and tested its pH, it would be a neutral molecule, okay? It's very deceiving. A lot of students want to say that amides are basic because they have that nitrogen functional group. But I want you to recognize the difference between an amide and an amine. Amides are not basic. Also, as we discussed previously, the nitrogen positioned right next to the carbonyl is a great electron donating group. So when you compare nitrogen as a donator, it's a better donor than oxygen. We know this. Why? Well, oxygen's more electronegative, therefore it's greedier, so it's less willing to share. Nitrogen is less electronegative than oxygen. It has a lone pair, and since it's less electronegative than oxygen, it's more giving, it's less greedy, so it's a better donating group. What this has an effect on, ultimately, is the electropositive nature of the carbonyl next door. That carbonyl right next to it, because of its donation, is less positive. So carbonyls of amides are less susceptible to attack by nucleophiles. They're not super attractive to nucleophiles because they're not hugely positive. So this nitrogen diminishes the electrophilicity of that carbonyl. That's why they're placed way at the end on the reactivity scale for reactions of carbonyls. However, we have lots of enzymes and processes for catalysis in our bodies. And generally, if you have an amine like this and an acid from an amino acid. So here are two amino acids arbitrarily. Okay, we'll say that they're different. The reaction of the amine part for one amino acid in an in, up, ultimately down and out with the OH as water leads to the very important amide, or as biochemists call, peptide. This is a peptide bond. That is a peptide bond. Organic chemists call that whole functionality an amide, but a biochemist calls the bond between the carbonyl and the nitrogen of the amide the peptide bond. Once you start linking one amino acid to another, to another, to another, ultimately making a polymer of amino acids, it's called, the long chain of amino acids is called a peptide. So direct your eye to the top right of the slide. Amino acids, represented by these circles, combine in long chains called peptides. And then once these peptides are long enough, they start having intermolecular forces guiding their folding and bending and twisting. One part of the chain is attracted to another part of the chain. This could lead to beta-pleated sheets, where they organize such that they're attractive intermolecular, it could be hydrogen bonding, could be ionic, could be, but there's attractive forces that perfectly pair to give a beta-pleated sheet. Or if it's a tighter intermolecular force attraction, it might kink to make a helix. These are called secondary structures, right? So primarily you get the peptide together, but then they start folding and bending and form these, when you take a step back, go, oh yeah, it's a helix. Oh yeah, it's a beta-pleated sheet. Take another step back, how these helices and beta-pleated sheets interact with one another is called the tertiary structure. And this is what comprises a protein. A protein is the peptide twisting and folding into these secondary beta sheets and helices, and then the protein ultimately is really just taking that one last step back and looking at the overall structure, the tertiary structure, how these helices and beta-pleated sheets also interact with one another and come together to form the ultimate protein. So amides play a large role in biochemistry, and you'll see them utilized. And I think it's really important from a functional group. If you take anything away from Orgo 2, it's distinguishing the difference between an amide functionality and an amine functionality. Amides play a large role biologically in lots of other areas, in natural products and polymer chemistry. Anandamide, I put this one in because I'm a lover of chocolate, is found in small quantities and is a neurotransmitter. It's a fatty acid neurotransmitter, and it's basically, it interacts with the part of your brain that THC, which is a marijuana ingredient, also interacts with. So it has this, this nature of adding to this receptor site that has to do with, appetite regulation, pain, pleasure, reward. And so just think about it. I'm just rationalizing and justifying my love for chocolate and how it is a chemical obsession for me. Interestingly, the word anandamide comes from a Sanskrit word, ananda, which means joy, bliss, or delight. So appropriately named in my view. Now, what are these amides? How do they undergo? What reactions do we see for these amides? Well, this first one that we're going to look at is very akin to the reactions we've been looking at thus far. We can convert the amide back to the carboxylic acid through hydrolysis. Hydrolysis, again, just being acid and water. If your reagents are acid and water, you're doing a hydrolysis. Okay, so what happens first? Knee-jerk reaction, acid-base chemistry. We are now going to empower the electrophile. We now have a very fully charged electrophile. The weak nucleophile, the water, does an in and up. We're in reversible conditions because we could have easily go in either direction, as we saw when we were doing carboxylic acids. We added OH2, so we could reverse out because the atom that we're using, the nucleophile here, is an oxygen, not a hydrogen or a carbon, so it is reversible. So that's why we're using the arrows, the reversible arrows. So at this point, we have to do some more acid-base chemistry after our in and up. Acid-base chemistry, this is our proton shift so that we can effectively write a nice and tidy Now I get a little lost, as you know. I got to remember that I'm driving off the nitrogen and I'm driving on the water. I know this because it's an equilibrium reaction. I have control and I'm driving oxygen on, right? So I'm driving the oxygen on, I have the control because Le Chatelier's principle gives me that control. It's an equilibrium. I could reverse out, right? So I can control it using equilibrium to help me along. Okay, so now that I've done acid base in up, acid base down out. This helps me remember, oh yeah, it's the yellow I'm driving off. I'm driving the nitrogen off. So and it doesn't matter which oxygen you pick, they're both OH, you'll get to the same spot. But just to make things look nicer, I'll use the top one and drive off the NH3. Now we were under acidic conditions anyway, so it's not surprising that we end up with a carbonyl that's protonated. But we did drive something off that is different. Remember, amides are neutral. Amines, which is what we generated, are basic. So before we even touch this reaction to a workup, it's probably going to do its own acid-base chemistry to buffer as the amine is being generated, to buffer the acid we originally put in. So there's already some self-buffering. You still probably have to do some workup to get the pH exactly to where you want it, but ultimately your final product is going to be a carboxylic acid. You will have driven on the water and driven off the NH2. This looks exactly like what we've been doing up until this point. Okay, so what's the deal with this one? Isn't this just in, up, down, out? Well, it is. It's a 1-2 addition, but notice that I wrote tricky here. This one's tricky, so we got to pay attention. And let's go through the mechanism, and then I'll show you how it differs and why it gets a note of tricky. We're reacting this amide now with a hydride source. Notice the arrow. The reagent is the H- source from the lithium aluminum hydride. So my nucleophile is non-reversible. Once I put a hydrogen onto a carbon, that thing is not popping back off. Okay, so that's the first thing to take note of. That's one of the reasons why it's different from the last reaction we just looked at. Now this is where things are tricky. You'll say, oh, but don't you just do down and out? Because this was in and up. Don't you just do down and out? Yes, but not how you think. Let's go back to this first slide. I specifically told you that nitrogen was a better donator than oxygen due to the difference in electronegativity, due to greediness issues, right? Nitrogen's a better donor, more willing to give than oxygen. You with me? Okay, in the solution here, I can only do this once. I've only got one time to get it right. This is not a reversible, oh, I can drive it in one direction or the other thing. This is a one and done. We have to do what thermodynamics tells us. We've only got one shot. Okay, so we're going to just maneuver some protons around. Okay, and it probably gets protonated through the solution. I'm not going to worry too much about where it gets the proton. I'm just going to shift its protons. Okay, it's like a proton shift. Somehow we're going to get to a point where in the solution, I'm just doing, this is just for my sake, right? I'm just shifting the protons for my sake to make things nice and tidy. So now, because I have a choice, O- could have come down. Now this is what people tend to do. This is the mistake. They come down and they kick out, and then they end up with the aldehyde. And then they do one more H-, and they end up with the alcohol. After workup, they get to the alcohol. This whole thing in blue is wrong. You have to proton shift. You have to stop because it's not reversible. And because nitrogen is a better donator, I'm not driving it on with Le Chatelier's principle. No, nitrogen's a better donator. It's always going to donate down and out. I'm going to keep it in blue here just to show you the difference. What I've just made is an amine. But amines are susceptible to hydride reduction. So it keeps going, right? So this is the down and out. And this step, this right here, is the tricky part. This is the part that you have to pay strict attention to. From here, it's not tricky. Amines, they get reduced like anything else with another in and up. So another H minus comes in and goes in and up. We end up with a nitrogen minus again, 2 hydrogens, and then upon workup, NH2. Now, can you see how getting to the NH2 versus the OH is very off, okay? So don't do down out with oxygen when you have an amide under non-reversible hydride conditions. Those are wrong. Okay, I also want you to notice, to kind of take a step back and look at what we did. Carbon 1, carbon 2 in the amide was the carbonyl. Carbon 1, carbon 2. So I'm just going to redraw this. Carbon 1, carbon 2. When you do this reaction, ultimately what you get is this. This is the overall reaction. Look at that overall reaction. Doesn't it look like we erased the carbonyl? Right? So what I want you to recall is that we had methods of taking aldehydes and ketones and doing Wolff-Kishner. To get rid of the carbonyl. We also had methods of taking a carbonyl like ketones and aldehydes, turning them into the thioacetal, and then hydrogenating them away to get rid of the carbonyl. So I want you to recall back in the ketone aldehyde chapter, we had a method for getting rid of the carbonyl and leaving the 2 groups that flank the carbonyl. And then the carbon in the middle is there, but it's completely reduced with hydrogens. Went from two bonds to oxygen to now 2 hydrogens. Effectively, reducing this amide has the same type of effect, but you can't do Wolff-Kishner on an amide and get rid of things the same way as we saw for ketones and aldehydes. So if you're thinking, oh, I need that Wolff-Kishner type reaction for an amide, reducing an amide using LAH is actually the way to go. You could, I guess you could kind of think about going back to carboxylic acids and reducing them gets you to the alcohol. So you can almost think about it as reducing them to alcohols, or think of them as getting rid of that carbonyl, but keeping the carbon infrastructure, including the OH. So it's kind of interesting. All right, so where are we? We have now completed all that you see in green here. We've also, I put it in red because that's the only tricky one that you're bound to get stuck on. My advice is on an exam, find the amide reactions with hydrides so that you are in the clear. You can get that one, done and dusted so that you don't get tricked by it when it's kind of peppered somewhere in the middle of your exam. So find that amide one so you don't get tricked in the middle when you get on a roll with the in, up, down, out trends. All right. I am not going to show you the amide to the nitrile. That's with SOCl2. It is in your textbook if you're interested. I'm going to finish with the last 2 arrows. We're next going to do a nitrile reduction using hydrides. This one is, after what we've just seen, pretty straightforward. Here's your nitrile. Let's do the H- version first. This is the 1,2 addition. We go in and up. We can start off right off the top because our nucleophile is strong and irreversible. carbon, double bonded nitrogen now. Okay, it can't come down and out because you've got a hydrogen and a carbon on either side. So you're kind of stuck here, right? And so, but you do have more of like a carbonyl species here. So under these conditions, it finds some way to gain a proton, and then another H- ensues. Upon workup, you end with NH2, right? So we'll call this carbon. I'll make this a carbon group. Carbon 1, carbon 2, carbon 1, carbon 2, and you end with this amine. Okay, so we have now done the hydride from the nitrile to the amine. You could have also done a hydrogenation. I mean, after all, it is a pi system. So we could consider it with a transition metal as a Sin4 across a triple bond. It just, one of the atoms of the triple bond is a nitrogen. But we're not really inventing anything new here. We go back to our alkene-alkyne chemistry, syn addition of a hydrogen, and then you just repeat it. Another hydrogen-hydrogen addition across the pi bond. And so it's basically a double Sin4. Sin4, Sin4. Which is the same as what we did when we reduced it with the hydride. Nothing new here, just conversion of a nitrile to the amine. This last one is how to get from a nitrile to a carboxylic acid. So let's draw that over to the right. Through hydrolysis. So we're looking at this top case from a nitrile to the carboxylic acid. And this is a repeat reaction. Okay, this is a repeat flashcard, but I'll go through it again. We could have this nitrile, acid-base chemistry. Just like a carbonyl, you have a knee-jerk acid-base reaction. And now we add our weak nucleophile, our water. Goes in and up. OH2. We're going to do some H plus shifts. So if you get into the swing of things here, okay, we had our in, up, proton shift. Now, down and out would be the next thing that you guys do. And it's okay if you do it. You're just writing a few extra steps, but that's okay. If you're in the flow of things, right, just do it. Reminding yourself that since this is an equilibrium, right, we're going to be driving off the nitrogen. Why? Because we're driving on the water. Le Chatelier's principle allows me to take control. I can circumvent the, oh, who's a better donator? No, I can go in either direction because it's reversible. I can back out. I don't have to do the thermodynamic thing, right? And so at this point, I have to just remind myself it's hydrolysis. I'm driving water on. So I'm going to, you could do this down and out. This is one option, or at this point, you could just do your second in up. So let me show both. I'm going to show you this is the down and out. Now you have NH2 double bonded to an oxygen that's protonated. Now, if you look at that, you just turn your head to the side. What I've just made is an amide. The amide is protonated. Take a look at that. It's a protonated amide ready for oxygen to attack. Let's go back to the slide we started with. An amide that's protonated. I literally just made this molecule, a protonated amide ready for water to attack. So from here on out, it is the exact same thing. This is why I did that extra step, because I think it's worth seeing that it's something that we've already done. Okay? You could say, well, do I have to do this step? No, you could have simply just added the water at this point and gone in and up. This gets you to NH2. Again, reminding yourself what you're driving on, and reminding yourself what you're driving off. So either way, you're going to get to the same species. Either way you do it. Water in and out. And you get to this thing here. You just have to remind yourself you're driving water on. Hydrolysis tells you so. So maybe you should change your flashcard. It's reversible, right? And so we've got the last few steps, which is a proton shift, acid-base chemistry. We're driving off the N, so we're going to make it NH3, OH, OH, reminding what we're driving off, reminding what we're driving on, driving water on, and now we're going to do the final down out. Pick an oxygen, it doesn't matter. Down and out. We drove the water on, we work it up, and again, because NH3 got knocked off, it's an amine, it buffers, it's going to do some acid-base chemistry, probably even before you work it up to give you the carboxylic acid. Okay, I would argue that this last step is the part that becomes a little bit less reversible. Okay, so now we've completed that last step in our explosion chart. I'm not doing the SOCl2. I've showed you the tricky one in red. There's only one left remaining in this crazy chart of ours, and that is from the anhydride back to the carboxylic acid. And I've highlighted this in yellow, okay? The line that we've got to fill in and we don't have a flashcard for is in yellow. This is not hard, and it's, guess what? 1-2 edition all over again. So I just urge you to try it on your own. I also want you to give this a try. Reacting nitriles with a Grignard, which are totally doable. So these are reactions that we didn't formally go over, but you guys can do them. You can predict the product. Okay, so I'm showing you the product, and I'm asking you to fill in the mechanistic how of how to get there. And you guys can totally do that. I also have a reagent sequence down here, starting with the chiral bromide species, and I'd like you to fill in the intermediary species as the reaction progresses. This is interesting as well. Nitriles can reduce to the aldehyde. So this is the product starting from this nitrile I want you to come up with, based on what you know about the reagent dibal that you saw with esters. I want you to show the mechanistic or propose a mechanistic sequence for how it goes from a nitrile to an aldehyde. Again, we didn't formally talk about this, but you can derive mechanisms based on the reactions that we've covered already. Here I have you starting with an ester and trying your hand at reacting the ester with a varied number of reagents. So predict the products. And lastly, in the middle, you start with the carboxylic acid and just a little practice on what the products are going to be given the reagents. So I know there's a lot of reactions in this chapter, but I hope that you see that there's a common trend, and there are really a very small number, if probably two I can think of, that are just a little bit more you have to pay stricter attention to as you figure out what the products might be.